and gentlemen. Time for another exciting episode of Rocks and Minerals. This one is about mineral classification. Now, if you remember in previous episodes, we talked about the elements and we looked at the periodic table. I remember there's 118 elements in the periodic table, but only 92 elements are naturally occurring. The rest are all synthetic, made in the laboratory. But if we look further, it turns out that we're talking about the Earth's crust. Only about 8 elements make up most of the Earth's crust. About 98.9% of the Earth's crust is 8 elements. And those are oxygen, which is almost 50%, silicon, over a quarter, then aluminum, iron, calcium, sodium, magnesium, potassium. And all the rest make up only about 1% or so. And it turns out that you only need a few elements to make up most of the Earth's crust. But they actually can combine to form compounds in many, many different ways. There's thousands of different compounds. So, and it turns out most elements are compounds. So, and they're driven by the outer valence electrons. So, it turns out all the atoms want a full shell. So if you look at the periodic table here, if you look at the far right there, the last column, column 18 or 8A, helium, neon, argon, krypton, xenon, they all have full shells in the outer shell, in the valence electron shell. And that's what all the elements want to be, but only the noble gases actually do that. I'll just show you an example here. Helium. You notice helium has 2 electrons in its shell. So it's perfectly happy the way it is. And the next one here is neon. You notice neon is 2, 8. So it's 2 in the first shell, 8 in the second shell. So it's perfectly happy the way it is. It doesn't have to react with anything. Next one here, argon. It has 3 shells, but you notice it also has 8 electrons in its outer shell. So it's all full shells, and they're perfectly happy the way they are. Now, if you contrast this with, by the way, they call this the Octet Rule, that all the atoms want to have 8 electrons in its outer shell. But it turns out that if you look at some of these elements, like, let's go down the periodic table here, like in the far left, for example, like number 11, atomic number 11, sodium, or number 19, potassium. Here's sodium. You notice sodium only has 1 electron in its outer shell. So it wants to have either, it needs to either gain 7 electrons or lose 1. Well, I already say it's easier to lose 1 electron. So it's going to get rid of 1 electron, calling it donating an electron. And it's going to be a positive ion, which is called a cation. And another example here is going to be, let's see, what is potassium? See, potassium is very similar. It's right below it in the periodic table. It also has 1 electron that it's going to donate. It's going to become a positive potassium ion, and which they call a cation. Now, if we go to the other side of the periodic table, you'll see like column 7A or 17, you have fluorine, chlorine, bromine, iodine, astatine. They all have, I'll show you, let's look at some of those here. Here's fluorine. You notice fluorine has 2 in its inner shell and then 7 electrons. So it needs to add 1 electron to meet the Octet Rule. And chlorine is right below it in the periodic table, and it's exactly the same. It has 7 electrons, and it's going to do is try to get 1 more electron to make the Octet Rule work. So what happens is these atoms will form bonds with other atoms, and it turns out that there's actually 3 different ways it could form bonds. I think this is the page here. There's 3 kinds of bonds. There's ionic bonds, there's covalent bonds, and then there's metallic bonds. But we'll go talk about each one of these here. So what happens with ionic bonds, the ions of opposite sign attract each other. So for instance, we talked about before how sodium, what it'll do is get rid of 1 of the electrons, become a cation, and then chlorine will get rid of 1 electron, will add 1 electron and become an anion. And what they'll do is, there you see this is the ionic bond. They will bond to each other. You know, positive and negatives attract. You know, the sodium donates 1 electron. The chlorine picks up the electron, and they're now happy. And of course, we know that this is sodium chloride. And the exact same thing happens with potassium. If you look at potassium, let me see if I can find potassium here. Potassium will do the exact same thing. Get rid of the electron, and it'll combine with the chlorine also, and you also end up getting potassium chloride, which, by the way, is a mineral called sylvite. The sodium chloride is a mineral called halite, which we know is salt, and the potassium chloride is sylvite. Now, these are all part of the halide group. So we're getting back to how we categorize these things. And so that's the halide group, and that's because they are using the anions from the halide group, from the halogens, fluorine, chlorine, bromine, iodine. So anyway, the next bond we're going to talk about here is the covalent bond. And this is where atoms share an electron. And let me just give you a couple examples of covalent bonds. If you go back to our hydrogen atom here, you notice it's got one electron, and it's a neutral atom, but it wants to have two electrons of none, two hydrogen atoms, and they actually will share their two electrons. And as far as the atoms are concerned, the nucleus of the hydrogen atoms think that there's two electrons. They both think they have two electrons, and they're perfectly happy with what they have. So that's a covalent bond. I'll give you one more example of a covalent bond, and this one is if you take the hydrogen that has one electron, and if you take carbon, let's take a look at carbon on the periodic table. And you notice carbon is in group 4A, and it's atomic number 6. So carbon has, if we look at the electron configuration, it has 2 electrons in the inner shell, and the outer shell is 4 electrons. Well, how does it get to 8? We could either add 4 or gain 4 electrons to get the right number. So it turns out that this periodic table here shows the oxidation states. And there's a lot of choices it can have there, but it could either have become a +4 ion or a -4 ion, or some other choices as well. Carbon will combine with hydrogen. It'll take the one carbon, which has 4 electrons in its outer shell, and then the hydrogens will come along and have 1 electron in its outer shell, and they will actually share one of the electrons with a hydrogen atom. And that's called actually a gas called methane gas, and that's CH4. And that's a perfectly good arrangement here. And by the way, when it finally forms these things, you notice it's like on 2 dimensions. We drew these things, you know, the H is on the top, and then one's on the bottom, one's on the left, one on the right. They're trying to be as far apart from each other as possible. Well, in 3 dimensions, the ideal arrangement is actually a tetrahedron. It's called a tetrahedron shape. And you notice it's got the carbon is in the middle, and then the hydrogens are around it in kind of a pyramid shape. And what they're trying to do is be as far away from each other as possible. And that's the tetrahedron of the methane. And by the way, methane is an organic compound because it has carbon in it. So if you start with carbon, hydrogen, oxygen in it, they're organic compounds. And there's a whole science of organic chemistry. And in fact, it's the basis for life on Earth is, at least the kind of life that we know, like mammals and reptiles and plants, is carbon-based. I'll do one more example of a covalent bond here. And I'll use silicon here. Now again, we look on the periodic table. I'll look at this one again. This one shows the oxidation states. And notice atomic number 14 is right below carbon. So it has almost the same electron configuration in the outer shell. So I'm see if I can find, where is silicon? Here's silicon. Right? You notice again, it has 4 electrons in the outer shell. So I could do something very similar to carbon, is form these compounds. So it turns out if I take a look at, let's take a look at oxygen here. Let's look on a periodic table first. On the periodic table, oxygen is grouped under 8. Right? So it's basically 2 groups away from being neon. So if I look at the oxygen electron configuration, it's got 6 electrons in the outer shell. So what it wants to do is add 2 electrons. Now if it does that, it's going to have a -2 charge. So now if I take the silicon, which has 4 electrons, I could actually hook up silicon this way. You see the silicon will be in the middle, and it'll have 4 oxygens around it. And again, these oxygens are, each oxygen is -2 charge, right? Because it has 2 extra electrons. So times 4 oxygens is -8. Well, the silicon will be +4. It'll get rid of 4 electrons. And then we have, everybody's happy there. And it turns out it's very similar to the methane. This the silicon, by the way, this is called silica, this here, and it's an ion, a silica ion here. And this will have covalent bonds, and you'll see how the silica in the middle has 8 electrons, so it thinks it has a perfect octet, but also the oxygens have the same thing. They look like they're also surrounded by 8 electrons. And it turns out they also will form a tetrahedron shape with the silicon in the middle and the oxygens at the corners there of the pyramid. So there's our tetrahedron structure for the silicon. So that's the different kind of bonds. The last bond we have is called a metallic bond. And this one's kind of hard to understand. Basically what happens is for metals, let's just take a look at one of the metals here. Here's like copper. It's in column 11. It's in group 11. See, it's atomic number 29. And it's copper's electron configuration. See, it's got 3 full shells, and then the last shell has 1 electron in that shell. So what copper is going to do, when if it's going to form a crystal with other copper atoms, it's going to get rid of that electron, kick it out, and it'll form a lattice structure with another copper atom just like it and a whole bunch of other copper atoms. And meanwhile, the electrons will be kind of just like flowing around them, and they're kind of shared by all of them. And you end up what they call a sea of electrons. So you have all these copper ions with all +1, but they're all surrounded by a sea of electrons. And the electrons are kind of shared by all the atoms, all the copper ions. And by the way, this is why copper is such a good conductor. If you put an electric field across this, all the electrons will start to drift in one direction, and you get a current flowing. So anyway, it turns out that if we go back to copper here, it's got 1 electron. If you go down below it in the periodic table is silver, number 47, and below that is gold, number 79. So if you see here, they have almost the same electron configuration. They're larger, but they all have 1 electron in the outer shell. There's silver, and there's gold. So they do exactly the same thing. And that's why silver, gold, and copper, they all kind of act very similarly to one another. Now, talk about one other thing here is, we're talking about these oxidation states of, no, this is the wrong page here. Oxidation states. So we talked about oxygen having 6 valence electrons. It wants to gain 2 electrons to become an oxygen -2 ion, right? And meanwhile, hydrogen has 1 electron. It'll want to get rid of that, become a hydrogen plus ion. Well, it turns out if those 2 things met up somewhere, they would actually form it's kind of like a compound. It'd be an OH, and they'd get together. But these things aren't complete in itself. So there you see in the upper left there, the oxide ion, the oxygen -2, it's got 8 electrons. And on the bottom in the middle, you have the hydrogen ion, H+, got no electrons. Well, it could connect with a covalent bond with a hydroxide, form a hydroxide ion, so an OH. And you notice since it's got a -2 for the oxygen ion and a +1 for the hydrogen ion, it'll have a -1 charge. And this is called a hydroxide ion. And now it turns out, suppose you had one of these hydroxide ions just floating around. And let's take a look at aluminum here on the periodic table. Aluminum is atomic number 13, right? And let's take a look at aluminum's electron configuration. And you notice it has 3 electrons in the outer shell. So it really wants to have, do better than that. So it turns out that what happens is aluminum aluminum can actually bond with this hydroxide ion, and it'll do it 3 of them. And aluminum will be perfectly happy. It'll be aluminum with 3 hydroxides. And by the way, this is called aluminum hydroxide, and it's also called the mineral gibbsite, which is in the hydroxide group. So we're back to how do we categorize minerals. So that's the hydroxides. So let's get to the next slide here, is how do we categorize these minerals? So minerals are classified. Now, there's over 4,000 known minerals, and we need a way of classifying and organizing them. So they're classified by chemical composition into groups. And now I put them into these 12 groups here. I got this from my book that I've reviewed, and I don't think there's any standard order for putting these into a particular order, but I ended up with these 12 here, and I've just labeled them here, picture here. It's sulfate, native elements, sulfide, sulfates, oxides, hydroxides, halides, and number 7 I've got carbonates, then phosphates, chromates, titanates, and molybdates, then borates and nitrates, then sulfates, then silicates, and finally the last one is mineral alloys, which actually isn't a mineral. So that's the way we classify minerals. And now it turns out that some of the groups are very large groups, and they have further subdivided by either the element or crystal structure into subgroups. So this is what basically where I'm going to end right now. And this is the first part of the mineral classification.